Howdy. This chapter is going to be over linked list and binary search trees. Linked lists. A linked list is a data structure where each item keeps track of the next item in the list. Each item in the list is called a list node. A node will store data and the next list node. When we build a linked list, it will keep track of the first node and last node. With only these two nodes, we can perform all the list operations. And when we get to the example section, this will become more clear on what this means and how this stuff actually works. Here, real quick, this is just the code that I'm going to be giving you for list node, private data. And like I said, a list node is actually going to store the next list node, which seems a little bit weird having a list node store a list node. Then we have our constructors, our accessors, and our mutators, and that's about it. A linked list will have two attributes. It'll have a list node first and a list node last. Constructors. We're going to have a constructor for a linked list that sets the first and last node to null, or we'll also have a constructor that creates a linked list with one piece of data. So this one will create a new node with the given data, and then first and last will become that new node, because that node will be both the first and the last node in the list. The methods we're going to have to write: get first, that one's pretty easy, it just returns the first node. Get first returns the value of the first node. Then we have one that returns the actual first node. Then we have the same thing for last. We have remove first, it would remove the first node and return its value. We have remove last, does the same thing. Add first, we're going to send data, it'll create a new node, add it to the list, and that new node will be the first element now. We have add last, we add a new node to the list with the given data, and it becomes the new last node. Clear empties the list. Size tells you how many nodes, how long the list is. Empty returns true when the list is empty. Get, you send it an index and it returns the value at the given index. Remove x removes the item at the specified index and returns its value. Add, this is our insert, add at this position this value. Set, go to this position and change the value. So we're making a linked list that will have pretty much all the commands that an array list has. Types of linked list. We have a basic linked list, and the next of last is null. So the last element has nothing after it. We have a circular linked list in which the next of the last element is the first. So the last is the end, but if you go past the end, you come back around to the first. We have a doubly linked list where you not only store the next item, you also store the previous item. So the next of last is first. The next of last is null, and the previous of first is null. So each item stores who's after him and who is before him. A double circular linked list combines both these ideas. For the double circular, you keep track of your next guy and your previous guy. And the next of last is first. The previous of first is last. So it's circular in both directions. All right, so we're going to do an example of a linked list. And with a linked list, we have two nodes. We have first and we have last. They both start out being null. So there's nothing in either one of these items. Now let's go ahead and do add first. So I'm just going to do this. Add first 6. And I'm going to show you what it looks like when I create a node. So I'm going to box it out. I'm going to put 6 null. Its next item is null and its current value is 6. We're going to say this is at address 47. Now let's look at the code of what actually happens when we do an add first. When we do an add first, we need to make a new node, and first and last should become that node. So let's go ahead and make a new node. Node A equals new node 6. So now we have a node that has the value 6. Then we would say first equals A. Last equals A. Because we only have one node in the list. This is the first, and it's the last. So what we do is we change first to be equal to 47. So let's just go ahead and write it over here. This guy is a 47. That guy is a 47. This is the memory address of where that node lives. First and last happen to be the same value. Let's say I do add first 7. What I'd need to do is I make a new node that is 7 null. Then what I do, maybe this guy has an address of 42. I say, well, your next is no longer null. We say his next is the number 47. Basically, that would mean his next is that guy. Then we would say, hey, first, you're not 47, you're 42. So this is the first guy, and we didn't change last. So this guy would be the first, this guy would be the last. Now let's assume we didn't add last. Add last 3. If we didn't add last, we would need a new node that stored null 3. And maybe he has an address of 17. So what we would do is we would say, hey, last guy, the guy at 47, your next is no longer nobody. It's 17 because he's after you. That would link the current last to this node. Now, last shouldn't be 47, it should be 17. And we have a first and a last node. We have no direct access to this item, which is at position 1, because this guy is at position 0. This guy is at position 1. This guy is at position 2. And this is our list. How we access the guy at position 1 is first we have to start at 0 and ask him for his next node. If we ask that guy his next node, it would be last. This is how we're creating a list with memory addresses. And we do not actually have an array list. We have 2 nodes, a first and last, that help us navigate through our list. And with those 2 nodes, we can do anything we want to in the entire list. We could get X, we could change X, we could add something to the end, we could add something to the beginning. And that's just a real quick walkthrough of what you're going to be doing in the lab where you're creating linked lists. Do realize that they get more complicated than this. Some are circular, where the last node points to the first. Some are double, or some are double linked lists, where you not only keep track of your next guy, you also have to keep track of your previous guy. The code gets a little complicated with this stuff, and we'll have a while to get our labs done. Trees and binary search trees. A tree is a data structure where the nodes store other nodes below them and a value. We'll be working with binary search trees. A binary search tree is a tree where its nodes store a comparable, a left node and a right node. The left node will contain a value smaller than the current node. The right node will be a value that has the value that is larger than the current value. A tree node looks a lot like a linked list node, but it has data, and then it has a left and a right tree node. Then we have accessors and mutators for each, and we have a constructor. Terminology. So how trees are going to work is you have one item at the top, and then there's going to be something to the left, something to the right. Those things will have something to the left, something to the right. When you build it, you're going to see on the next slide, or in a couple slides, it kind of looks like a tree, but it's an upside down tree. So the top is the root, A child is any node stored directly by another node. The parent is the node that stores another node, the child. So a parent has children. So the two things below it are children. If you go directly above a child, you get to the parent. Depth, the number of steps it takes to access the node from the root. Descendant, a node that is more than one level below another. And we're going to see on the next slide a graphical depiction of this stuff. Ancestor, a node that can access a given node, the descendant, and is two or more levels below it. Above it. Leaves, nodes that have no children. Now let's look at this. See, here's the root of the tree and it starts branching. So this is the root. It has a child of the root has a child of 3 and a child of 2. All these other items are descendants of 1. These items down here are called leaves because they have no children. 15's parent is 7, 11's parent is 7. 7 has a child of 11 and 5. 3 has children, 5, 7, and descendants 9, 13, 11, 15. And notice how this works. Oh, this is a sample tree. This isn't a binary search tree. This is just storing left and right. In a binary search tree, all the items on this side of the tree would be smaller than 1. All the items on this side of the tree would be larger than 1. So when I do my examples, I'll be doing a binary search tree. So this is an older picture that I didn't realize wasn't the binary search tree that I used to use. But this is just an example of a tree where you have left children and right children. So when I do my example, I'll make sure that the example is going to be of a binary search tree, not a basic tree. A transversal. A transversal is the visiting of all nodes in a tree. This is what the transversal method will look like, and it's recursive. If you get to null, that means there's nobody below it. Otherwise, transverse left, then transverse right. So I'll go through how that transversal works on paper when I do my examples. We have different types of transversals. A preorder prints the value of a node when it is reached. In order prints the value of a node after the left child has been processed. Post order prints the value of a node after both of its children has been processed. So in general, when you go through a tree, you go left, left, left till you can't go left, then you work your way back up, and then you go right, right, right till you can't go right. So let's walk through this. Here, I've been to 8. On a pre-order, I print it as soon as I get to it. I've been to 8. So I go left. I print 3. I go left. I print 1. I come back up. I've already done the left, so now I go right. 6. Then I go left. 4. Come back up. I haven't printed 7. I print 7. I work my way back to the top of the tree. Now I go right. 10. 14. 13. Work back up, and I'm done. Now if we transverse the list in a in order, you only print a node when you come up from the left. So I'm going left, going left, going left. I just finished the left side because it has no left side, so I print 1. I print 3. 4's left side is done, I get to print him. 6's left side is done, I print him. 7's left side is done, I print him. Now I print 8. Then I print 10, because his left side is done. Then I print 13 because his left side is done. Then I print 14 because 14's left side is done. Work my way back up, and I'm done. For a post order, you only print after you've processed all children. So I go this way. I print 1. I print 4. 7. Now I can print 6 because I've done both children. Now I can print 3. Cannot print 8 yet. Nope, nope. Yes. So I print 13, 14, 10, 8. And that's how my orders work. And notice what I did here is I actually created a binary search tree. Because here, to my left of 8, I have something that's smaller. And everything on this whole side of the tree is smaller than 8. Everything on this side of the tree is bigger than 8. So 3, on the left side we have something smaller. On the right side we have something bigger. So we follow the rule of if it's bigger than you, it goes to the right side. If it's less than you, it goes to the left. And that's what a binary search tree looks like. All right, attributes. For a tree, we store one thing, a tree node, root. Constructor. We're only going to have a basic one that sets the root to null. Methods. We're going to have string methods that return the pre-order, the in-order, and the post-order transversals. We're going to use these for printing our trees. When you're testing to see if your program's working right, you're going to need to do a pre-order, an in-order, and a post-order. With the combination of all three, you can tell if the structure of your tree is correct. We're going to have a min value method. It returns the smallest value in the tree. We're going to have a max value that returns the largest value in the tree. We're going to have a max depth. It'll tell you how deep the tree is. So it returns the depth of the lowest item in the tree. Clear sets root to null. Size returns the number of items in the tree. You're going to have to do a transversal to get the size. Empty returns true when the tree is empty, false otherwise. Contains. It'll check to tell you if a value in the tree is there. Insert. Attempts to add a value to the binary tree. Returns true if it was added. Returns false if it's not already there. So we're going to be holding unique values in our tree. Add. Attempts to add the value to the binary tree. Returns true if it's added. The exact same thing as insert. Just have two names. Remove. Attempts to remove the value. Returns true if the removal was successful. And here's some notes on how to remove. If a node has no children, replace the node with null. A node has one child. Replace the node with its child. If a node has two children, swap the data of the node with the smallest right descendant. Now properly remove the value from its new location. So this is kind of a recursive process. I'll try to go through it more when I'm doing my examples to show you how this stuff works. Binary search trees keep track of one node called the root. In a binary search tree, the root will start at null. When we add new elements, each element will have a value and a left and right. So let's go ahead and do add 4. So when we add 4, we'll get a node that will have null on the left, 4, null on the right. This might be at address 42. Then we would say root equals 42. All right, next. Let's say we wanted to add 7 to this list. Because we're working with a binary search tree, we're going to need a new node that stores the value 7 and has nobody on the left and nobody on the right. Null, null. Let's say this guy's at address 49. Then what we do when we go to our root, we say, oh, 7 needs to be added. It needs to go to the right. I have nobody on the right, so I need a new node. And that new node is going to be my right node. So this would have the address 49, linking these. If I needed to add a 3, we would follow the same procedure, but we'd say, oh, 3 is smaller. My left guy's null. So we add 3, null, null, and maybe it has address 5. So then we change this null to a 5. Now we have a left child and a right child. Let's say we wanted to add something like 5 now. Or let's say we add the number 6. Add 6. We would say, oh, 6 is bigger than 4, but it's less than 7, so it would have to be to the left of 7. So we're going to make a new spot. Maybe it's got 6, null, null. It might be at address 106. So then we say this guy's left child is address 106. And this is the basics of how a binary search tree works. We can't have the same element twice in a list. If we do, we just don't add it. Anybody left of something is smaller. Anybody right of something is bigger. Adding and removing gets more complicated, And sorry, adding's not too bad. Removing is its own monster. And in the lab directions, I'll tell you the steps you follow to remove. It's a recursive method. It's pretty nasty. There are lots of different cases for how to remove. So I'll cover that in the lab directions, but this is the basics of what a binary search tree does. All right, thanks.